In this video, we're going to talk about the plastic deformation of polymers. As with most parts of polymer mechanical properties, this depends strongly on temperature, and that's because obstacles must be overcome for plastic deformation to occur, and those obstacles are more easily overcome as the temperature is higher. We're going to mostly focus on the plastic deformation of amorphous thermoplastics, although at the end we'll look briefly at how plastic deformation occurs in semi-crystalline thermoplastics. So for these amorphous thermoplastics, we're going to go through and talk about several different temperature ranges. One important note, though, is that the sort of stated temperature regions are for a rather large strain rate, so a testing time of just a few seconds. If the test time is longer than that, so the strain rate is slower, that would be sort of equivalent to shifting the temperature upward. So as with all high temperature plastic deformation, the strain rate and the temperature are interconnected in determining the behavior. So let's start and look first at what's happening far below the glass transition temperature. So when we're far below the glass transition temperature, the bonds between the molecules are still strong and the specific volume is low, so the chains can't really slide. So as a higher and higher load is applied, the molecules are straightening viscoelastically. And because the chains can't move, if the load continues to increase, then brittle failure will occur. So not really plastic deformation, but we'll have brittle failure occur essentially by breaking the intermolecular bonds. As the temperature gets a little bit higher, then more plastic deformation can begin to occur. So now we're going to consider temperature slightly below the glass transition temperature. So this would be a temperature of about 0.8 of the glass transition temperature. And now these amorphous thermoplastics have some limited ductility. This ductility is a result of the fact that the mean distance between chains is larger now, and this enables them to partially overcome the binding forces, giving the molecules at least some mobility. It's important to note, though, that unlike metals, polymers do not work harden during plastic deformation because no new obstacles are created as the molecules slide past one another. During plastic deformation at these temperatures, there are microscopically small lens-shaped cavities that form in the material, and these are called crazes. In the slides that follow, we'll take a look at how crazes form, how they evolve during continued deformation, and what their size is. Let's start by looking at how they form. So crazes typically form at surface defects, such as scratches or impurities. Because of these stress concentrations, the material will soften slightly just at that point. As a result of this stress concentration and the softening, plastic deformation will occur around that area. Then what happens is that there's a slight local necking. So there's a local necking at the point where the plastic deformation is being concentrated. The stress state goes up there and generates, as a result, the formation of cavities. So we have all of these individual cavities here that are forming locally in the material. These might be on the order of maybe a few nanometers. In between the cavities, then, there is locally a heavy load. As a result of the higher load in between the cavities, then we get more plastic deformation and essentially the extension of the cavities at the same time. So then the cavities are extending, and in the areas in between the craze, we're seeing the straightening of molecules. The last step is that the areas in between the cavities turn into what are called fibrils. So let's take a look then at what the craze looks like and sort of what the dimensions of this feature are in the material. So this top figure here shows the cross-sectional view of the craze. They have a thickness of between about 1 to 10 microns in the material. The overall diameter of the craze is on the order of 10 to 1,000 microns, so up to a millimeter. And they're bridged by the fibrils that we just talked about. So these fibrils are making the bridge, and the fibrils themselves are on the order of 10 to 100 nanometers, maybe, and are spaced at a similar spacing, so 10 to 100 nanometers, depending on how the cavities formed. The volume fraction of the fibrils in the craze is between about 10 to 50%. A couple of things to note about these crazes is that the thickness of the craze is independent of the applied stress, but does increase as the temperature goes up. It is the case, however, that if there is a larger stress, there will be more crazes. So this second figure down here is showing sort of a partial edge view of the craze. So these would be the fibrils, and since there's no top here, you could imagine that these are broken fibrils, but they might be connected to a top surface. So these are sort of the fibrils that are in the center of the craze. And then over here, you can start to see how it is that the craze grows wider. And so on the next slide, we'll talk about the growth process for a craze. So the growth process for crazes occurs through a process called the meniscus instability, and it's illustrated in these images here. So at the edge of the craze, there's a stress concentration, and that's what drives the further growth. So essentially what happens is that at the edge of the craze, these sort of finger-shaped extensions evolve and contract, and in the process they form new fibrils. So here we see this instability arising, and it becomes magnified here as these sort of center regions continue to withdraw, and these get smaller, and so the stress builds up even further. And so essentially these sort of fracture, and they leave behind new fibrils. So that's how the craze gets wider. It can get a little bit more open because the chain molecules are aligning. And then in the end, the fibrils that are in the center of the craze break. So the formation and growth of crazes is one way that plastic deformation occurs in amorphous thermoplastics. The second way in which plastic deformation can occur in amorphous thermoplastics is through the formation of shear bands. So here we see a representative stress-strain curve for an amorphous thermoplastic under compressive load. So shear bands are going to be more commonly forming during compression, plastic deformation and compression. But we see that we start out with the linear elastic region, and then we have the formation of shear bands. So at the beginning of the formation of shear bands, there's actually some softening in the material. But as the deformation continues, then we start to see sort of a strengthening again. And you can see here in figure B, the shear bands are forming first with a low density, but then with a higher density. And so as the higher density of shear bands comes about, they are interacting with one another and making that deformation harder to occur. One thing to note about shear bands is that these will tend to form at an angle between 45 to 60 degrees with the load direction, as illustrated in figures B and C there. At the molecular level, what's happening in the shear band formation is illustrated down here. So we have these chain molecules and we are applying the shear stress in this direction. And what happens is that essentially the chains sort of line up, but at this angle with respect to the load. So the chain molecules themselves are shearing. They either will straighten out or will form two kinks in the process of doing this. And as I said, this results in a region that has aligned chains. So in terms of which deformation mechanism is going to occur, it depends on the loading, the time, and the temperature. Compressive loads are more likely to have shear bands, whereas tensile loads are more likely to have crazes. Also, large strain rates make it hard for the shear bands to form, and so crazing is also more common under that deformation. So we had been looking at temperatures around 0.8 of the glass transition temperature, and now we're going to look at what happens really close to the glass transition temperature in these amorphous thermoplastics. So as we continue to increase the temperature closer to the glass transition temperature, the chains become more and more mobile. We can see what happens in this figure where we're looking at a stress strain curve for an amorphous thermoplastic. So we start with an elastic region, and then after the yield strength is reached, then a neck forms due to local softening. And so that's illustrated here. In step B, we have the formation of the neck, and then that neck grows while more and more molecules are drawn and straightened in parallel. So meanwhile, while that's happening, we have sort of a very long elongation of our polymer at essentially a constant stress. And so the chains are straightening out. As we eventually get to this point here, now more of the covalent bonds are actually carrying the load. Eventually then we come to the point in the stress strain curve where the polymer molecules are oriented and then the stress starts to increase significantly. This is actually a process that is sometimes used strategically to draw the thermoplastic in order to manufacture a material where the chain molecules are arranged in parallel. An example of where this is done is in aramid fibers. Aramid fibers are used often in composite materials, and these can have a yield strength of 4.7 GPa, so that's really quite high, and a Young's modulus in the fiber direction, so parallel with the fibers, of up to 450 GPa. So this can be used strategically to actually generate an aligned polymer. So the very last temperature region to look at is what happens when the glass transition temperature is exceeded. So in the previous video, we already looked at what happens at temperatures above the glass transition temperature. Now we're assuming that there is also a load applied. And in that case, the mobility is very high, and with the applied load, the chains are going to very easily slide past one another. This is due in part to the fact that the specific volume is high, and also that there is melting of the intermolecular bonds. In this case, these amorphous thermoplastics behave similarly to highly viscous liquids, and therefore they essentially have no strength at this point. So we have been primarily focusing on the plastic deformation behavior of amorphous thermoplastics, and I just want to end by considering how the plastic deformation occurs for semicrystalline thermoplastics. So a couple of important things to note before we get into this figure of semicrystalline thermoplastics is that in the crystalline region, the bond strength between chains is higher than in the amorphous region due to the smaller bond length. This also increases the Young's modulus and the strength in those regions, even when the temperature is above the glass transition temperature. So, when we have plastic deformation of the semicrystalline polymer, this is sort of what it looks like. So we have these crystalline regions here and then amorphous regions in between. And plastic deformation starts by lengthening the amorphous regions. So the crystalline regions don't change as much because they're more strongly bonded, but the amorphous regions do extend. Then what happens is that the crystalline regions start to realign to be more parallel to the loading direction. And then finally, the crystalline regions start to separate into blocks. So at this point, you're starting to break some of the bonds in the crystalline regions. And then essentially towards the end, then you have the formation of these microfibrils. Because the amorphous regions are amorphous, it's more likely that they would be where you would find impurities or short chain molecules, and therefore the interface between the amorphous and the crystalline regions can be weak, and if cracks were to form in the polymer, that's most likely where they would occur. So just to conclude, I do want to mention about the plastic deformation of elastomers and duromers. These both have very small amounts of plastic deformation because the crosslinks prevent molecular sliding. In the case of elastomers, if they're used above the glass transition temperature, they can be deformed with elastic strain, but not really with plastic strain. And finally, in the case of duromers, these are essentially brittle because there are so many crosslinks in there, and so the covalent bonds between the chain molecules break. And so we have now talked about the plastic deformation behavior of amorphous and semicrystalline thermoplastics and wrapped this up with how other polymer structures deform.